Next, we will discuss how to use normal distributions to approximate the probabilities for binomial distributions. Let's consider the following example. Historically, there is roughly an 80% chance that a person of age 20 will be alive at age 65. Suppose that 10 people of age 20 are selected at random among those who purchased a life insurance policy. The insurance company may want to know the probability that the number of policyholders that are still alive at age 65 is exactly 6, at most 4, or at least 8. To start the solution, let's introduce a random variable x that represents the number of people that are alive at age 65 among the 10 people that were selected. Then x is a binomial random variable with parameters 10 and 0.8. And the following probability distribution table can be constructed using the following formula that was covered in the section for binomial random variables. Now, using the probability distribution table, we can answer the questions. The probability that x equals 6 is equal to 8.81%. The probability that x is less than or equal to 4 is equal to 0.64%. And finally, the probability that x is greater than or equal to 8 is equal to 67.78%. For most real-world problems, the number of people under investigation is much larger than 10. Consider the same problem, but let's suppose that 100 people of age 20 were selected at random, and the insurance company may want to know the probability that exactly 75 of them will be alive at age 65, or at least 83 of them will be alive at age 65. To start the solution, let's introduce a random variable x that represents the number of people that are still alive at age 65 among the 100 people that were selected. Then x is a binomial random variable with n 100 and p 0.8. And the following probability distribution table can be constructed using the formula for binomial random variable. Now, using the probability distribution table, we can answer the questions. However, we run into a problem very quick. Finding the probability that x is equal to 60 requires enough computational power to handle large factorials and large exponents. At the same time, computing the probability that x is greater than or equal to 80 requires even more computational power. So we have an interesting situation. We do know how to find the answer, yet we cannot compute it without a powerful calculator. Is there another way to find the desired probabilities without a powerful calculator? The short answer is yes. So let's scale back to the problem with a sample of size 10. And let's consider the probability histogram along with the probability distribution table. Recall that the probability histogram serves exactly the same purpose as the probability distribution table. That is, we can read the probabilities from the histogram itself. For example, on the histogram, the bar that corresponds to x equals 6 has the area equal to the probability of x equals 6. Next, to find the probability of x greater or equal to 8 means the same as to compute the area of the bars at 8, 9, and 10. Similarly, to find the probability that x is less than or equal to 4 means the same as to compute the area of the bars at 0, 1, 2, 3, and 4, which are virtually equal to 0. This principle is true for any discrete random variable of any shape, and in particular it is true and can be applied for a binomial random variable with any parameters n and p. Does the overall shape of the histogram remind you of anything? Yes, it does look like a normal probability density curve. But which values of mu and sigma give us the best approximation? Recall that a binomial random variable with parameters n and p has the mean and standard deviation that can be computed using the formulas. Now, it is not surprising that a normal variable y with the same mu and sigma as the binomial random variable x has the probability density curve with the same shape as the histogram of x. In other words, the probability density curve of y can be used to approximate the area in the histogram for x. In our case, we have a binomial random variable x with parameters 10 and 0.8, whose mean is 8 and standard deviation is 1.26. Therefore, if we let y be a normal random variable with parameters 8 and 1.26, then it can be used to approximate x. So now that we know the parameters of the normal variable that approximates the original binomial variable x, we can focus on using it to answer the original questions about x. While it is natural to approximate the probability that x is greater than or equal to 8 with the probability of y being greater than 8, by doing so, we will be ignoring the area of the left half of the bar at x equals 8. A better estimate can be obtained by finding the area to the right of 7.5, which is equal to 0.6543 and is very close to the actual probability that we found earlier. The adjustment of subtracting 1/2 from the boundary is called the correction for continuity and must be done to obtain the best estimate. Now, while it is natural to approximate the probability of x equals 6 with the probability of y equals 6, by doing so, we will be ignoring the fact that the probability of y equals 6 is equal to 0. A better estimate can be obtained by finding the area between 5.5 and 6.5, which is equal to 0.0933 and is very close to the actual probability that we found earlier. In summary, for a binomial random variable x with parameters n and p, and a normal random variable y with properly computed parameters, the following approximations can be made. The adjustment of adding or subtracting 1/2 is called the correction for continuity. Note that the approximation becomes less accurate for skewed binomial distributions, so we only perform it when both np and n times 1 minus p are greater than 5. Similarly, we can make the following approximations using the correction for continuity. Let's go back to our original problem when we used 100 people instead of 10. This time, instead of looking at the probability distribution table, we will compute the mean and standard deviation of x by using the formulas. And then we define y as a normal random variable with parameters 80 and 4. Now, using the normal random variable y, we can answer the questions. The probability that x is 75 can be approximated by the probability that y is between 74.5 and 75.5, which is equal to 0.0457. Also, the probability that x is greater than or equal to 83 can be approximated by the probability that y is greater than 82.5, which is equal to 0.2660. These approximations are expected to be very close to the true values because both np and n times 1 minus p are greater than 5. We discussed how to use normal distributions to approximate the probabilities for binomial distributions. While this result is not as significant now as it was prior to technology becoming accessible, it still highlights the importance of the normal distribution in nature and applications.